All right, so I guess I'll go ahead and get started. There's no one else here, so we will continue. Last time we spoke, we had just completed example 29.5. I have a little bit about chapter 29 that I want to finish up, and then I want to have a little bit of a discussion of one issue uh, in chapter 30, and then something about 31. I'm going to go ahead and sort of knock that out right now. So let me start by sharing my computer or my iPad screen. All right, so I've just shared my screen. There's now one person in here, so thanks for coming out, Alex. I've already started just because no one had showed up, so I just went ahead and started. We're looking at example 29.6, and I mentioned how I will be doing a little bit more in chapter 29. Then I'm going to jump into 30 and 31 really quickly. I want to show you some of the things that are required of us for chapter 29, or excuse me, for chapter 30, and then I want to show you the bare minimum, just some stuff to refresh you guys regarding 31 and actually give you some information that you didn't have. In this example 29.6, which is a continuance of 29.5, which is the last example we worked last time, it says, suppose 100 loops of wire shown below are connected to an EMF that produces a counterclockwise 60.0 milliamp DC current in the wire. When the square coil is pulled from the magnetic field, what then is the current in the wire? So what's going on here is as we're pulling it, we figured out that basically a induced current is occurring. That induced current turned out to be a clockwise current. Y'all should try to verify that now to make sure y'all understand how to use Lenz's law properly. And that clockwise current was in fact 15.0 milliamps. The way we calculated it was E induced is equal to negative N d phi b over dt, which is Faraday's law. But we also used Ohm's law to replace E induced with I induced times R. And of course, R was the 100 ohms resistance of the 100 loops, and I is the induced current, N is the 100 loops, B is the strength of the magnetic field, which is 0.600 Tesla. L is the length of the square rectangle and the width of the square rectangle, and V is the velocity that the rectangle was moving to the right. And we calculated that velocity by realizing that it would move such that its entire length moved completely outside of the magnetic field, even though it started with its right edge lined up with the right edge of the magnetic field. The left edge would just exit it after 0.100 seconds. So that meant it moved 5 centimeters in 0.100 seconds. When I did that calculation, you see the velocity was 0.500 meters per second. So putting all those numbers in to I induced R equals N times B times L times V gave us the 15 amps. But what we're seeing here is we now have a connected EMF. So what you might imagine, for instance, is a battery as one of the wires. So the wires are going around 100 times. Maybe one of those trips, it actually has a battery between one end of the wire and the other part of the wire. So you could just imagine cutting through one of the strands of the 100 loops of wire, and then taking one end of the wire that you cut and connecting it to the negative side of the battery, and connecting the other end of the wire you cut to the positive side of the battery, and that's going to produce a 60 milliamp current. But that 60 milliamp current is in the counterclockwise direction, so it's actually in the opposite direction as the induced current. So that means the total current, I total. Actually, I should probably work this in blue. I'll do that. I'll change my ink color. So solution, the I total, at least while it's still moving, is equal to 60.0 milliamps minus 15.0 milliamps equals 45.0 milliamps. And from that, what they're asking specifically is when the square coil is pulled from the magnetic field, what is the current in the wire? So that's your actual answer. It's 45 milliamps while moving through the magnetic field B. So that's part of the answer. Now, the other part of the answer is you got to understand that once it actually gets completely outside of the magnetic field, once that left hand side of that ring or that rectangular, in this case, square loop, is completely outside of the magnetic field, then no more current will be induced, and the current will jump back up to the 60 milliamps that the battery was able to provide. So, I hope that helps you. And that's sort of the understanding of how you're going to treat the things like back EMF and that sort of stuff. You haven't yet learned exactly what the calculation is required to calculate that back EMF, but we will learn that specifically the voltage, which is a back EMF that you get is I, or excuse me, it's L, the what we call the self-inductance times d I dt. So L d I dt is the magnitude of the induced, or excuse me, of the EMF, that the back EMF that would be created. So that's a term that we're going to use later in chapter 30, though I'm not going to do much with chapter 30 because we're running out of time. So there's example 29.6. I want to go on to 29.7. This is an application of that same equation that I just used. So, for instance, we found last time that the induced EMF was E is equal to N times B times L times V. So we know that we're going to make use of that. But in this case, excuse me, but in this case, uh, I'm going to read the problem and let you see what we're going to do with it. It says an airplane. Sorry, I keep yawning, and that's not helpful to me maintaining a train of thought at all. So, anyways, let me turn on the chat window. I got two more people that just came in. Feel free to go ahead and chat me your first and last name. But 29.7 says an airplane travels at 1,000 kilometers per hour in a region where the Earth's magnetic field is about 5 times 10 to the negative fifth Tesla. And and is nearly vertical. What is the potential difference induced between the wing tips that are 70.0 meters apart? So, what we're using here is this equation right here. E is equal to N times B times L times V. That's one we derived last time, and we're going to use that repeatedly. I think it's even one of the equations that appears on the equation sheet, so it's one that you can use. If you don't see it on the equation sheet, then it's one you have to memorize. And in principle, since it's not on if it's not on the equation sheet, but again, I really think it is. But if it's really not on the equation sheet, that means you can't use it unless you derive it first. So be careful with that for my testing. Now, with that in mind, all we've got to do is go ahead and calculate what this N times B times L times V is. But in this case, the N is just one. And in fact, we don't actually have a complete loop. We just have a sheet of metal basically that you can sort of picture the wings as. So the current's going to tend to try to go around the wing in some sense, and depending on which direction the magnetic field is pointing, which direction the plane is flying, all that good stuff, you can discern whether it's going to go in a loop around the wing in a counterclockwise fashion or a clockwise fashion. But we're just not given enough information to do that. So for this case, n is equal to 1, but we can say E is equal to 5 times 10 to the negative fifth Tesla, that's the magnetic field strength, times the actual L, which is 70.0 meters, times the velocity, which is 1,000 kilometers per hour. But remember, we can't use units of kilometers and hours, so we have to say, well, there's 1 kilometer in 1,000 meters, but we also have to say that in 1 hour there is 3,600 seconds. So ultimately, what we're going to be doing is taking that 1,000 and dividing by 3.6, and that'll give us the velocity in meters per second. So 5 times 10 to the negative fifth times 70 times 1000 divided by 3.6 gives me on the order of 0.9722 volts, and that means it's really just because this is an estimate problem, it's really about 1 volt, and that's it. So that should allay some of the fears you might have for your knowledge of stray voltages and the fact that jet fuel is so explosive and that sort of thing. You might worry about something like the magnetic field developing a voltage difference, and then a voltage difference could cause a spark, and then a spark could actually cause an ignition. But it seems like the voltage, even at 1,000 kilometers per hour, even with a 70 meter long wing, is not going to be more than on the order of a volt. Anyone have any questions on that? All right, so now we're going to do example 29.9. It says force on the rod. To make the rod of figure 2912A move to the right, this is the figure that I've got drawn for you right here. To make the rod of the figure move to the right at constant speed v, you need to apply an external force on the rod to the right. Explain the and determine the magnitude of the required force. That's part A, and part B. What external power is needed to move the rod? Do not confuse this external force on the rod with the upward force on the electron shown in figure 2912b. Okay, so what we're going with here is we're trying to calculate the force on the rod. So we're specifically asked explain and determine the magnitude of the force. So as this rod, the blue part, moves to the right, the area is actually increasing. And since the area is increasing and the magnetic field goes through all of it, that means the flux must be increasing. So Lenz's law tells us that if the flux is increasing, then an induced current will be created in an effort to oppose the change in flux. So it's going to try to reduce the flux by creating a magnetic field pointing in the opposite direction of the existing magnetic field. That means that the induced EMF is going to try to generate a current pointing into the page because the current, the magnetic field that exists right now is pointing out of the page. So if we imagine taking our right hand and poking our fingers right in the middle of that hole between the blue bar and the curved black bar, then that is the direction of the magnetic field. Now, if I take my palm and wrap it around that bottom wire, I'll see that my thumb points to the right, and that dictates that our induced current will actually be in the counterclock, or excuse me, in the clockwise direction like this, and that means also like that. So that's the direction of the conventional current. It's going in a clockwise fashion. Now, the equation that we have regarding force on a rod moving in a current, carrying a current moving through a magnetic field is F is equal to I times L cross B. Now, we had done this as dF is equal to I dL cross B, but in this case, we don't have to do any integration or anything because the magnetic field doesn't change significantly. The the direction of the wire, nor the direction of the current, the I and the L don't, nor the magnitude of the current really doesn't change significantly. So we see the I, which points downward in the blue rod, and the L, which is supposed to be a vector that points the same direction as conventional current, it also points downward. And we see the magnetic field is perpendicular to that. So that means the magnitude of the force would just be I times L times B. Now we can use that and we can say the force is in fact I times L. We know L is actually the lowercase l. We know B is the actual B, but we have to figure out what the current is. What we do know is that E induced is equal to I induced times R. I'll assume that's the current of the whole rod slash wire system. And then I'm going to drop off the negative sign because we're just looking at the magnitude here, but that's going to be N times B times L times V. Again, we don't have a number of turns here. We only have N equal 1. So I can go ahead and say that I induced is going to be equal to N. Oh, actually, N is 1, so I'm leaving that off. It's going to be B times L times V over R. So there's my current, and then I'm multiplying that by L, and then I'm multiplying that by the magnetic field. So the force is actually going to be uh, B squared L squared over R times V. B squared L squared over R times V. And that's it. That's the actual force. Now, what direction is that force? Well, we use our right hand rule. IL is the first vector, and that we use our index finger for, and the magnetic field is the second vector, and we use this finger for that. Remember, it's going to be 0 if the angle between my index finger and my middle finger is 0, and it's going to be 0 if the angle between my index finger and my middle finger is 180. But other than that, it'll be good to go. In this case, we actually got 90 degrees, so life is good. So I'm pointing this downward, which is the direction of the current in the blue part of the wire. Now I've got to turn my hand this way so that my, or excuse me, no, this way, so that my middle finger points out of the page. And now I see that, in fact, the force generated as a result of this current carrying wire moving to the right is actually going to be to the left. So there's going to be more or less a force trying to keep the blue bar from moving to the right. It's actually pulling to the left. So I'll say F is this, and it points to the left. Hopefully y'all all can see that, and I wanted to take the time to write it so that you can look later and make sure you can come up with the same result. But that is, in fact, the force. Now, the other part of the question wanted to know what external power is needed to move the rod. So what we know here is power is equal to, there's a bunch of different ways you could do it. You can say P equals IV, you can say P equals I squared R, or you can say P equals V squared over R. I'm going to use P equals I squared R like that, and that's the power. So power is equal to I squared R. We already figured out that I is, in fact, B times L times V over R. Now we're going to square that and multiply it by R, and lo and behold, you're going to get B squared L squared V squared over R squared times R. That R is going to cancel out with this R right here, and that's going to give me B squared L squared V or V squared. So B squared L squared V squared over R. Oops, wrong color. So this is equal to B squared L squared over R times V squared. Now, another thing you might remember is P is equal to F times V. So if you remembered that, then you should be able to figure out that F should be P over V. And if I did that, you would get B squared L squared over R times V, which is exactly the same force that we got before. And that helps us confirm that this is clearly the correct result. So yes, this is the power dissipated, and that power would be dissipated. I went to say, I went to subscripted R, and I wrote a subs. I actually wrote the R instead of the letter P. So, anyways, that's the actual result. Anybody have any questions on that? Okay, looks like no. I'm looking at the chat just to make sure. So the very next part that we have here is electric generators, and I want to talk a little bit about that. I just want to give you the equation so you'll know how easy it's done. You could expect, for instance, a chucker type problem, which is more or less just you plugging into the formula. So I'm going to work out that formula for you so that you understand it. And then I'm going to work out the transformer equation, which is how we make transformers. For instance, we know that the most efficient way to send electricity to neighborhoods from power plants is to jump the voltage up super, super high. So if you see those big, tall, almost look like humans without arms or heads, they're towers going through country fields and mountainous fields, and they look like a human that just has pretty much two shoulders and a torso and two legs, but have no head. And then the wires go up where the head would be, and sometimes over where the shoulders would be, that sort of thing. Those wires are often carrying anywhere from 100,000 volts to 200,000 volts to a million volts. And the reason why they bump that voltage up so high is it turns out that from P equals IV, meaning when you actually step up the voltage in what we call a step up transformer, if the voltage goes up by a factor of 10,000, since power, you're not generating any new energy from this transformer, power that's in must be equal to power that's out. And since P equals IV, if the V goes up, like you do with a step up transformer, the I has to go down. So if you step up the voltage by a factor of 10,000, then you're stepping down the current by a factor of 10,000. And remember, P equals I squared R would mean, oh, wow, we're reducing the lost power by a factor of 10,000 squared, which would be 100 million. So that's part of why we do what we do in stepping things up and down like that. But to understand that, you need to know Faraday's law and then the transformer equation, which is easy peasy. So let me show you what a generator actually does. So your book actually has a pretty good figure of it. You can imagine a coil, a loop of wire, if you will, that's free to turn. They've mounted it on an armature, so they have a cylindrical object, and then from that center of the cylindrical object is like an axle sticking out both ends. And you could actually put that axle on bearings, and that would make it nice and smooth. And then you could use some mechanical methods to actually rotate that armature. But in order to do that, you have to have a wire on it, and you have to have the armature between two heads of magnets. So let me show you what I mean by that. In general, what we're thinking about is just a loop of wire, and the loop of wire we can look at like this. And I'm trying to draw it tilted, so that's why it looks a little disfigured, if you will. And what we're imagining in this scenario is that this is actually wrapped around a circular armature like this, and this is also around a circular armature like that. So you can imagine this wire as going along the little axle, and then it cuts across the circular surface here, and then it cuts along the cylindrical soup can label, if you will, and then it comes back along the cylindrical soup can label, and then it goes back across the circular face. That should be roughly at the center. I didn't draw it that way very well, but I'm going to put it here, and then you'll see, oh, okay, so this is the actual axle that should be turning like that, and this is the wire, and there's ways you can conduct electricity and allow this to spin without actually breaking the contact with it. So what we have to understand is the way I've drawn this is this wire, the one that's not bold, is actually back behind this cylinder so that we can't see it. So I'm making it dashed right now so you'll understand. And this part, of course, isn't there at all. And this part right there isn't there at all. And all we see now is uh, this circular part of the cylindrical armature doing all of this. And I'm trying to clean it up so my drawing looks a little less sketchy and a little more real. But the main thing is I need you to have some physical understanding of what this looks like in 3 dimensions so that you'll understand what's going on. So there's the actual cylindrical part. Again, we're not seeing anything but these cylindrical parts, which includes this right here. And I drew that a little too big before, so I'm going to try to shrink it down so that it looks like we're actually at the middle. And now that's basically the electric generator. So if you had some mechanical way of rotating this object, which we clearly have, again, these parts have to be dash because we're not actually seeing through the thing. But that's how the wire goes. And we use what's called slip rings, and slip rings allow current to flow from a wire, let's say, oops, not like that, from a wire, let's say, that connects to this wire. And then there's another wire that connects to this wire. And the way it does that is via slip rings. So that's something important. But basically, you can imagine a slip ring as if it's like a bracelet going across here. And because it's like a bracelet, it's constantly touching that wire that's spinning around. And this side also has a similar bracelet, only this bracelet only touches that other wire on the other side. It's got something that's non conductive up against the wire that's closest to me. So because of that, we get an area, and that area, of course, might be if this length right here is A, and this length right here from here to here is B, then the flux at any one point, depending on the magnitude of the magnetic field and the area, should be B times A times B times the cosine of the angle between the B vector and the differential area element vector. Remember, we represent the differential area vector as a vector that's perpendicular to the plane of the loop. And what's more is we could actually wrap this around. Instead of just being one wire, it could have N wires. The main thing is that E is equal to negative N d phi B over dt, which is Faraday's law, gives me, in this case, N is going to be 1. So I'm just going to go ahead and say N equals 1. This is going to be the negative of d by dt of the integral of b dot dA. And from that, we get negative integral of, or excuse me, negative derivative of b times, I'm going to go ahead and say a times b is capital A, times cosine theta, like that. And that gives us the derivative of cosine is negative sine, so that's going to make this plus b times a times the sine of theta. Now, if we assume theta rotates at a specific rate, we could say, or theta changes at a specific rate, we could say theta is equal to some angular speed times time. Then we would have the induced EMF is actually B times A times the sine of omega t, like that. And that's actually the formula we're going to use. If you wanted to go a little further, you could also say that that E, the induced EMF, is equal to N times B times A times, now what we got to do is remember sine theta. When I take the derivative of sine of, or excuse me, the derivative of cosine with respect to t, I get negative sine, but then I've got to take the derivative of theta with respect to t because that's the chain rule. So that's going to force this to become no longer BA sine theta, but BA omega sine theta, which is sine omega t. So that's the actual expression for induced EMF as a result of electric motor, basically like this. So if you just take this type of setup, and the one part I didn't draw on here, which hopefully you're looking at the drawing so it wouldn't matter, but the one part I didn't draw on here is technically we have to have a north pole of a magnet on one side and the south pole of a magnet on the other. So we could say this is the north pole of the magnet, and then that's just something you can't see. And then over here on the other side would be the south pole of a magnet. Whoops. The south pole of a magnet, which I'm going to put right here, say, and that's going to go up this way and be back down this way like this. So it's going to look like that roughly. And this is the south pole of the magnet. Now, I would actually ideally like to have that magnet exactly right up against that near that armature where it's not touching, but it's super close because magnets have a notoriously short extension. So that's really what's going to happen. And as a result of all this, you're going to generate electricity. You're going to generate, in fact, a AC signal, and the AC signal is going to look like this, which is just like, obviously, this is E, and that E is equal to, that was really ugly, that E is equal to N times B times A times omega sine omega t, like that. Uh, the peak voltage we might call E0, in which case this becomes E0 times the sine of omega t, and E0 in this case is N times B times A. Oh, excuse me, E0 times omega. Sorry about that. So it's N0 times E0 times omega sine omega t, where E0 is specifically equal to N times B times A. Now, what is that in terms of actual AC voltage? Well, AC voltage says that we use ERMS, and ERMS is the peak voltage divided by the square root of 2. So we would have basically that the, just threw me a curveball. Oh, yeah. Sorry about that. The omega has to be in there. It has to be in the E0. I don't know why. I looked up and I saw something. I thought maybe I wrote it wrong, but I didn't. It was actually written right the first time. So it is actually N times B times A times omega. So, oh, I know what it was. I looked at it and they put a omega between the B and the A, and I didn't realize that. So this is going to be N times B times omega times A over the square root of 2, and that's basically how you can generate electricity. So if you just find any particular mechanical energy source that could rotate something, then you can generate electricity. You might, for instance, take that propeller and connect it to a grist mill, like used to be done near rivers, and that's just a big, almost like a Ferris wheel, but you'd have a Ferris wheel sticking out the side of a building, and that Ferris wheel hangs in the water, and the water is a moving stream, if you will. That stream will just basically connect through surface tension and all sorts of stuff to that water, and due to pressure differences will rotate that wheel, and as that wheel rotates it's connected to the its axle is connected and is the axle of this armature, so that little armature will rotate in there as well. And of course, if the rotational rate is really really low, you're not going to generate much electricity, but you can compensate for that by making a really strong magnet, or by making a really large area, or by making a really large number of turns. All of that will result in electricity. So, simple type of problem you might want to solve, just so you'll have an idea of what I think is fair game, is this one right here. This is example 2910. Actually, it's not 29. No, it's 2910. So 2910 says an AC generator. The armature of a 60 hertz AC generator rotates in a 0.15 Tesla magnetic field. If the area of the coil is 2 times 10 to the negative 2 square meters, how many loops must the coil contain if the peak output is to be E0 equals 170 volts? So what we have here is the frequency F is 60.0 hertz, and I'm trying to lock that down as having two sig figs. The magnetic field, and notice since they said hertz, I had to interpret that as F, not omega. The magnetic field is 0.15 Tesla, which is pretty significant, by the way. The area of the coil A is equal to 2.0 times 10 to the negative 2, and they were kind enough to give us that in square meters, which is really nice. And we want epsilon zero, or excuse me, E zero, the EMF peak voltage, to be 170 volts, which is approximately what peak voltage is for the AC that we use here in America. Basically, 125 times the square root of 2 and 145 times the square root of 2, or 125 times the square root of 2 is about 176. So if you call it 125, you're thinking maybe 175. If you call it 120, then you're thinking maybe it's closer to 169.68. So that's where the 170 came from. And what they're asking us for is n equals question mark. Well, we know that E0 is equal to N times B times A times omega. So all we have to do is solve for N, and N will be E0 over B times omega times A. That's 170 volts divided by 0.15 Tesla times the 60 hertz has to give us omega, which omega is 2 pi times the frequency. So that's going to be 2 times pi times 60 hertz. And then all of that times 2.0 times 10 to the negative 2 square meters. So in the bottom, we get hertz times Webers, and a volt divided by hertz times Weber gives you basically, because a hertz times a Weber is in fact a volt, that cancels out and leaves just a pure number. So with this in mind, I'm going to say 170 divided by parentheses 0.15 times 2 times 3.14159. That's the 0.15 times 2 times pi times 60 times 2 times 10 to the negative 2, and close parentheses, and that gives me n is equal to 150.3 volts. And I just wanted to show you that if that number has a decimal point larger than zero, unless the number that's not zero is further out than maybe two or three decimal places, then you're pretty much going to have to go ahead and go for the full next one up. So I would report this answer to be 151. Your book's going to say it's 150, but either one is acceptable for me. Any questions on that? Okay, so that's the main thing, and they talk about alternators and all sorts of cool stuff, so you can understand really how stuff works. That's the main thing that I want you to get out of that section. But now I want to we're going to more or less ignore the section on back EMF and counter torque and eddy currents and that sort of stuff. Uh, you should read that and you should know, especially if you're thinking at all about becoming an electrical engineer. All of that's really important. There's a lot of neat applications you can use for that. For instance, there's a small company in Elizabeth City that I've worked for, and they wrap solenoids and then use those to be able to tell how rapidly something's rotating. For instance, the turbines in a steam turbine or the wheels of a railroad, of a train, all that sort of stuff. And that's all from these types of applications. But I want to go on to the idea of a transformer. So let me remind you that we started off this chapter with that little green ring, and it had a battery connected to a wire, and then the wire was wrapped around the left-hand side of the ring. Then on the other side of the ring, we had another wire that was wrapped around the right hand side of the ring, and then that was just connected to a galvanometer with no battery in it whatsoever. That is, in some sense, a transformer. So the diagram that I want to give you for a transformer is, I'm going to take, let's imagine that old belt buckle possibly you had in grade school when you did a Thanksgiving play. As good pilgrims, we all had our fancy belt buckles, and the belt buckle looked like this. So that's always been my story for my students. But what we can imagine is current coming in through this wire right here. So this is IN, and what's going to happen is it's going to go behind there and come back out and come back out and come back out, and so on and so forth. And what this would be N sub P turns. Okay. Not only that, we would argue, and this looks kind of funny, but this is common. This is what we call Vn or V primary. Just like NP means the number of turns on the primary side. Now, on the other side, we're going to have a different number of turns, like that. This side, the number of turns will be N sub S for N secondary. And of course, out will come a current. And again, we'll also have a output voltage V out, which equals V secondary. And there's going to be an outputted current as well. And that's related somewhat to it. But here's the big thing. We know from Faraday's law that E induced is equal to negative N d phi b over dt. If this belt buckle, which by the way should be made of, ideally it would be iron, which is ferromagnetic, and not only that, they would take the time to cut iron up into little thin plates, and then they would sort of glue them all together or laminate them, because the more breaks you have in the continuity of the iron, the fewer eddy currents you get, which can steal energy from the system. So to make this transformer as close to 100% efficient as possible, it's best to not use a big chunk of solid iron, but rather use a bunch of plates of iron, sort of assembled like a jigsaw puzzle to some extent, except much more regular shapes, and then laminated together. But the big thing is, if this is done fairly efficiently, then what we can say is that phi b on the primary side is equal to phi b on the secondary side, and that would suggest that d phi b on the primary side over dt is equal to d phi b on the secondary side with time. So what that means is E primary over N primary is going to be equal to E secondary over N secondary. And since we decided to use voltage, I'm going to go ahead and switch that to V and instead of the epsilon looking thing. So we're going to say V primary over N primary is equal to V secondary over N secondary. And more specifically, this is what we call the transformer equation. V secondary is going to be equal to N secondary over N primary times V primary. This is the transformer equation, and if NS is greater than MP, then this is called a step up transformer. Ooh, that was a really funny looking P that just happened there. This is a step up transformer. And that means the input voltage will be smaller than the output voltage. Now, if you also remember what I told you specifically, that power in has to be equal to power out, then you could say P primary equals P secondary. Now, that's best case scenario. That's 100% efficiency, which we don't get, but it's very, very close. In fact, Dominion Power and various other companies have made very, very efficient transformers. But the main thing is we can assume it's 99% or something like that just for the heck of it. But it's probably is pretty close to 99% or at least in the 90s. But the main thing is because of conservation of energy, if it is 100% efficient, then the power in the primary side will be equal to the power in the secondary side. And that means I primary times V primary is equal to I secondary times V secondary. Again, because P equals IV is the equation we're using there. Because of that, you can say that IS over IP is actually equal to, in this case, we're saying IS over IP. That's going to be VP over VS. And looking at that with respect to the transformer equation, we can see that VP over VS would actually equal NP over NS. Make sure I did that right. VP over VS is equal to MP over NS. So this tells us that I secondary over I primary is equal to N primary over N secondary, which means I secondary is equal to N primary over n secondary times I primary. And you see that the fraction is in fact upside down. So what is a step up transformer for voltage is actually a step down transformer for current. And I think within the field they try not to use the phrase step up and step down except when talking about voltage. Uh, at least I know my father practiced that, and he worked at Dominion Power for 30 some years. So, anyways, that's what you see. If you actually step the voltage up by a factor of 10,000, that means NS over MP is 10,000, and therefore IS would be 1 over 10,000 times IP, so it would step it down by the same amount. Now that we have that, and your book has a lot of examples to show you how much energy that saves, but the main thing in doing that is realizing that P is equal to I squared R. Now, you might also recall that P is equal to V squared over R, and I told you that we step up the voltage so that the current goes down, and I pointed at I squared times R as the voltage, or excuse me, as the power loss. Well, the difference there is you might say, well, what about V squared over R? The V squared, since we're stepping that up, that means the power is going to be even worse. Well, the voltage that the current is sent at is not the same as the voltage difference from one end to the other. One end to the other is the voltage drop from the power plant all the way to, let's say, the substation. That voltage is usually on the order of, a few volts. That's not the V that really matters. The 2,000 or 200,000 volts, that's the one that we're talking about. So do consider that when you try to work any of these problems. But let's look at example 13. So 2913 says the charger for a cell phone contains a transformer that reduces 120 volts AC to 5 volts. To charge the 3.7 volt battery. It also contains diodes to change the 5 volt AC to 5 volt DC. Suppose the secondary coil contains 30 turns and the charger supplies 700 milliamps to the cell phone battery. Calculate A, the number of turns in the primary coil, B, the current in the primary, and C, the power transformed. So let me write down what we know. We know that V primary is going to be 120 volts AC. We know that V secondary is going to be 5.0 volts. We know that the secondary coil contains 30 turns, so we're going to say N secondary is equal to 30. We're also going to say that the charger supplies 700 milliamps, so that means I secondary is 700 milliamps. What we're asked is for part A, they want to know N primary, so NP is equal to question mark. For part B, they want to know the current in the primary, so they want to know IP is equal to question mark. And then finally C, they want to know power equals question mark. So we're going to use the transformer equation, which says that V secondary is equal to N secondary over N primary times V primary. We already know that N secondary is supposed to be 5 volts, so we'll write 5.0 volts is equal to, we're asked for N primary, but we know N secondary is 30. So I would put 30 over NP there. And we know that V primary is 120 volts, like that. So that tells us that MP is supposed to equal 30 divided by 5.0 volts times 120 volts. 30 divided by 5 is 6, and 6 times 120 is 600, 700, 720. 6 times 20 is 6 times 2 is 12. 6 times 20 is 120. So yeah, it should be 720. So this should be 720 turns. So in primary is equal to 720 turns, like that. And that is part A. We're done there. I primary is, according to our equations, we know that I primary, well, actually, I'll just write it out as we have it. The equation that I gave you was I secondary is equal to N primary over N secondary times I primary, but we want I primary, so I primary is going to be N secondary over N primary times I secondary. So I primary should be equal to N secondary, which is 30, divided by N primary, which is 720. You can see that the zeros cancel out and I get 3 over 72. And then I know that the I secondary is 700 milliamps, and I can just leave those units fine. So what I'm going to do is take 700 and multiply it by 3, and then divide that by 72. And that's going to give me 29.17 milliamps. So the primary current that we put in is 29 milliamps roughly, and what we get out is 700 milliamps. Now, all we need to do is figure out what is the actual power transformed here, and power can be written as P equals I secondary times V secondary, or we could do I primary times V primary. Either one's fine. I'm going to go ahead and take I secondary times I primary. I secondary is 700 milliamps. V secondary is 5.0 volts. So this is going to give us something in milliwatts, if you will. Oops, someone else just came in. So when I take 700 and multiply it by 5, I get 3,500, and that's milliwatts. But we can get rid of that milli by dividing by 1,000, in which case we see it's 3.50 watts. So that's the actual power transformed here. And that's it. That's the kind of problem you should be able to solve from this chapter. That and the rest of these examples are pretty much all that you need to know. I want to jump real quick to chapter 30 to discuss what we would normally cover. But I think I'm just going to leave that part off for you guys because we just didn't have enough time to cover it. I would encourage you to look at the induction paradigm. So just do a search for inductance, inductance, on my YouTube channel, and you'll find where I take a process just like the process that I taught you about Gauss's law, where we take Gauss's law, use that to calculate the electric field. Let's say near an infinite plane, or near a infinitely long cylinder, or near a spherical surface that's charged. And then we say, okay, now let's figure out using that result, let's figure out what the electric field is between a positive flat plate and a oppositely charged flat plate, distance d apart, or in the case of a coaxial cable, a positive inner cable and a negative inner side of an outer cable. What's the voltage? What's the electric field between those two? Or in the case of spheres, what's the electric field between the inner sphere that might be positively charged and the inside surface of the outer sphere that might be negatively charged? What is that electric field? Once we had that, we use V equals negative integral of E dot dl to calculate the voltage difference between the positive and negative terminals of that capacitance. And then once we had that, we use C equals Q over V to calculate capacitance. That's the paradigm that I told you you guys should be able to do. Well, there's a similar one for magnetic fields, only we're not doing capacitance, we're doing what's called inductance or self-inductance. Okay, it's the symbol L. And the way we do that is we use Ampere's law to calculate the magnetic field around, let's say, a current carrying coaxial wire. And then we imagine that current carrying coaxial wire has a magnetic field outside of it. And then outside of that is another cylindrical shell of wire that has the current going the opposite direction, and that makes an inductance. And we use the formula for the magnetic flux, phi is equal to the integral of B dot dA, to calculate the flux through that coaxial cable. And then we use L is equal to phi, the magnetic flux, divided by I, the current, and that gives us the capacitance, or excuse me, the inductance in henries. So that's the paradigm that I would otherwise teach you, but we've just run out of time. I could go on and do it. I just don't think it's fair to do that and then test you on it immediately. So I thought it'd be better. I was going to go and cover a little bit and then just say you guys aren't going to be responsible for it, but I don't think I could even fit that in. And instead, what I'm going to do is jump to chapter 31 and show you a recap of what you need to know for this. So, chapter 31 is called Maxwell's Equations and Electromagnetic Waves. And I want to point out what Maxwell's equations are. We've learned Gauss's law, which says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. That's Gauss's law. Okay. Now, there is an equivalent to that in the magnetic field, and it's called Gauss's law for the magnetic field. But as I told you, magnetic field lines never come to an end. They always make a full loop. And if you see a magnetic field line that doesn't make a full loop, that's either in the process of forming a closed loop, or it's in the process of dying out and losing the closed loop. Because of that, that means specifically that there's no such thing as a isolated north pole of a magnet nor an isolated south pole of a magnet. So you can't have magnetic field lines that just die. They would have to die on a south pole of a magnet and then start on a north pole of a magnet. We don't see that. So the ultimate result is that the closed integral of B dot dA, notice I said B dot dA, in this case is actually equal to zero. So we call that Gauss's law for the magnetic field. So that's two of Maxwell's equations. There's also Ampere's law and Faraday's law. For Faraday's law, we might write it as E, but normally we write it as the closed integral of E dot dl. Notice I'd said E dot dl is equal to negative N d phi b over dt. That's called Faraday's law. Okay, that's Faraday's law. And I left off my W. And then there's another one for magnetism, and I'm going to write it under it because I have to use another name. The one for magnetism is called Ampere's law, and it's not quite correct. Right now, we know B dot dl is equal to mu zero times I enclosed. Oops. I don't like that I at all. Okay. As mu zero times I enclosed. That is sort of Ampere's law, but it's not quite correct. And this is what part of what made it ultimately these four equations be called Maxwell's equations. Because what Maxwell realized was that if you consider a wire running into the side of a capacitance, so let's imagine that this is our capacitor right here. Okay, then you have another wire coming out the other side like this, and technically speaking, you can't see that part because it's not there. And technically speaking, you can't really see this part because it's hidden by the plate. But the main thing is, if you took, for instance, an Amperian loop around this, let's take my green loop. If I took a green loop around here that's a circle that happens to be perpendicular to the wire itself. And I'm going to imagine, in fact, that the wire has a current I running that way. And then that would imply that we're going to take a Gaussian an Amperian loop that goes around it this way. So it's going down in front of the wire. It's going into the page below the wire, and it's going up behind the wire, and then above the wire it's coming out of the page. So that's the way we would typically try to apply Ampere's law such that the current would come out positive. But the way Ampere's law is actually written in terms of vector calculus, it turns out that that Amperian loop is just the boundary of a surface. And what you're supposed to be able to do is you're supposed to be able to calculate the current that goes through that surface. So again, not the loop, but specifically the surface whose boundary is that loop. So one of the surfaces that you could imagine as the boundary of that loop would be this little flat surface right here. And that's fine because the current clearly penetrates that, right? In fact, if I wanted to draw it accurately, I'd need to not show the magnetic field lines going back here, and I just need, for instance, the wire going here without those. So you can see, for instance, that the wire literally penetrates that flat surface. But what if we chose a different surface? What if we chose, for instance, Santa's bags? So imagine now that that loop, which was just now, it's the outer boundaries of like a little piece of rubber membrane, like a trampoline or something like that. Well, now imagine that it's actually the opening hole of Santa's bag. If that was the case, then we could draw Santa's bag like this and have Santa's bag go right in between the plates of this parallel plate capacitor. And this bag, for instance, would look like that and go through there, and it would look like this and come through here, and it would look like this and go through there. In that case, because that's literally an opening from a metal plate on one side, air or vacuum in between, and then another metal plate on the other side, no actual charges will jump across that space unless the capacitor fails. So in general, there's no current going through there. So there seems to be a contradiction. If I chose this red surface as Santa's bag, then the I enclosed would be zero. Yet if I chose the green surface, the I enclosed would be the I there, and I'd get B equals mu zero I over 2 pi R. But with the red bag, I'm getting B equals zero. So it's either true or it's not true. So what Ampere did, or excuse me, what Maxwell did was figured out how to fix it. For instance, we know that C is equal to Q over V, and we know that I is dQ dt. So we can solve C equals Q over V for Q, and we say Q is equal to C times V. Now we can substitute the capacitance of the capacitor, which is epsilon 0 A over D, where A is the surface area of the plate and D is the separation between the plates. And then not only that, the voltage would actually be the electric field times the distance. So that's going to be the electric field times D, like that. Now you can see that in this particular case, the D's cancel out. And if we wanted to know what would actually act like a current, we'd need to take the derivative of Q with respect to T. So this current, and we're actually going to call it the displacement current because that's what it's called historically. But it turns out the reason they called it displacement wasn't based on found ideas that turned out to be true. It turned out to be based on an old theory that didn't work out so well. So it's not that useful to know the name as a displacement current because it's not going to give you any insight into how it works. So don't try to waste any time on that. So I is supposed to be dq dt, but Q we just found, at least for this particular capacitor case, is epsilon zero A times E. Well, the epsilon zero is clearly a constant, so that can come out in front. But now we've got d by dt of E times A. Does anybody recognize what E times A looks like? Electric field strength times an area. Does that look like something we've run into before? Look at the left-hand side of Gauss's law. The left-hand side of Gauss's law is E dot dA. That's electric flux. So E times A is electric flux. So what we might say is this is epsilon zero d phi E over dt. Now, in order to have this current on the right-hand side of Ampere's law, I have to multiply it by mu zero because the existing current is multiplied by mu zero. So the fix to Ampere's law is plus mu zero epsilon zero d phi e over dt. And now it's Ampere's law with Maxwell's correction. If if it wasn't for Ampere figuring this out, electrodynamics wouldn't be complete. There's problems associated with this. You can't make a wave equation. There's a lot of things you can't do without that displacement current term. So these are the four Maxwell equations, and I tell my students you should be able to name them and state them verbatim at a drop of a hat once you've completed this course, and that's true here too. So just like I'm going to rehash all those things I told you that you should know, I'm getting ready to say them now, so y'all might want to take the time to record it. But basically, from the very beginning of 241, we learned Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, Newton's law of gravity. Then we went on and learned Kepler's first law of motion, Kepler's second law of planetary motion, Kepler's third law of planetary motion. You should know all six, or excuse me, all seven of those laws now verbatim. Additionally, we learned the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. And we also learned Kirchhoff's loop rule and Kirchhoff's junction rule. And now we've learned Maxwell's equations. So all of those things, as well as under what conditions is linear momentum conserved and under what conditions is angular momentum conserved, all of those things combined are questions that I can ask you at the drop of a hat, and you should be able to give it to me. And that's supposed to be the most pleasant gift I could give you guys. So please, please, please take the time to commit that to memory. And you should, just as a student that's finished a 2-semester calculus-based physics sequence, you should know all those things off the top of your head anyways. So work on that. Now, the other part of this is it turns out you can take these equations, and even if you get rid of the sources, specifically in Gauss's law, you'd have to get rid of Q enclosed. In Ampere's law, you'd have to get rid of I enclosed. But everything else would be exactly the same. And you can see because of that, we'd have to have the Ampere's correction or Maxwell's correction to Ampere's law because otherwise we wouldn't have anything but zero on the right hand side of Ampere's law. But it turns out you can take those four equations and combine them, and when you do, you get a wave equation. This is what a wave equation looks like. In general, and hopefully you remember this from chapter 15 and 241, but in general, a wave equation looks like this. It's the second partial derivative with respect to x squared or y squared or z squared. And it's going to be a derivative of something. And that was a big problem. No one really knew exactly what was doing the wiggling with regards to electromagnetic radiation, or what we ultimately just thought was heat coming from the sun. We knew that it had to be a wave of some sort, but we didn't know what was doing the wiggling. And not only that, we had never seen waves except in material. And as far as we knew, we thought space was a vacuum. So they invented the idea of the ether, assuming that was what was in the space between the planets and the stars and stuff. And ultimately, that experiment to detect that ether is what led us to the Lorentz transformations, which Einstein was able to derive reaching just from studying electricity and magnetism. So this is the left-hand side of the wave equation. The right-hand side is 1 over the square of the velocity of the wave times the second derivative of that same quantity, which we didn't know at the time, but this time the derivative is with respect to time. So that's what a wave equation looks like, and it has that little slot right there where the velocity is. When Maxwell put his equations together, he got an equation like this, and what he got was actually got two of them. He got the second partial of E with respect to x squared plus 1 over, actually, in this case, he ended up having mu 0. This is supposed to be equals, not plus. Come on now. Equals mu 0 epsilon 0 second partial E with respect to t squared. And he got a similar equation, second partial of B with respect to y squared is equal to mu 0 epsilon 0 second partial of B with respect to t squared. And at that instant, he took out his calculator. Well, you could say he took out his calculator because this is 1830s. Probably didn't pull out the calculator. But anyways, you calculate mu 0 times epsilon 0. You flip it over and you take the square root of it. And what you discover is 1 over the square root of mu 0 epsilon 0 is equal to modern day. It's 299,792,458.0 to an infinite number of decimal places meters per second, which he recognized, oh wow, that's the speed of light. And at that instant, he and only he on the planet knew exactly what light was. He's like, oh wow, here's the speed of light. I know what light is. And what light is this. It's an oscillation. Let's draw a line like this, say. It's an oscillation of a magnetic field and an electric field like this. So this part right here that I just drew is what we can imagine is the electric field. And then perpendicular to that is what we're going to call the magnetic field. And these are supposed to be the same magnitude and in phase and all that good stuff. This is the magnetic field. Like that, and these blue lines are the electric field, and that's, oops, I should have used blue there. Uh, the plane that the blue electric field is in fact called the polarization plane. So when you talk about polarized sunglasses, what you're talking about when you say polarization is in what direction does the electric field oscillate. So light often has a random polarization, but when light bounces off the surface of the water, most of the electric field perpendicular to the surface of the water gets absorbed into the water, so that then any existing electric field that survives is pretty much just oscillating sideways, left and right. Then what you have is horizontally polarized light bouncing off the ocean surface or off the water surface or off the pond surface. Because of that, if you're a lifeguard or a coast guardsman or someone that works on the water, it's pretty convenient for you to use polarized sunglasses, and polarized sunglasses are stretched during their manufacturing so that they can stop light that's horizontally polarized and just allow vertically polarized. So by only allowing vertically polarized light, that means you're cutting out most of the glare coming from the ocean surface. So if you actually want to buy sunglasses and you want to buy polarized ones and you don't want to get ripped off, what you should do is take your glasses and then take another pair, the pair that you want to buy, then take another pair just like them, not telling them which ones you're going to buy, but take them both. And in one case, hold the right lens horizontal and then put the right lens of the other one vertical right next to it. And try to look through both of them. If you look through both of them, you can see light, then they're not very well polarized. If you look through them both and they're at two different angles like this and you see light, then they're not really polarized sunglasses, or they're at least cheaply polarized. But that's what polarization is. And all of this was for me to tell you about what actual radiation is, electromagnetic radiation, which is, sort of the power that does everything to us now. Our Bluetooth, our Wi-Fi, all of that is electromagnetic radiation. And that means it's electric field oscillating in one direction, a magnetic field oscillating in the perpendicular direction, and then the velocity of the light is perpendicular to both of those, such that E cross B is in the direction of V, the velocity. So I'll write that down. E cross B is parallel to velocity. So that's really amazing. No matter what, at all times, E and B are perpendicular to each other in a particular sample of electromagnetic radiation. E and B will be perpendicular to each other. And if you take the cross product of E crossed into B, you get the direction of the velocity of propagation. Now, what is light? Well, I have a nice mnemonic that I say as an homage to Rush Limbaugh, who's no longer with us, but he's the person that got me all excited about politics, so I listened to him quite a bit. But the mnemonic is great excess undermines. Notice how I spelled excess with an X as opposed to a E. So great excess undermines various industries, Marxism rules, and that's because he says all teachers, especially college teachers, are communists. So that's what I'm referring to. But in addition to that, the visible spectrum can be opened up to not Roy G. Biv, because the Roy is red and the I is infrared. So you'd probably suspect the red and the infrared should be next to each other. Not only that, the V is violet and you expect the UV, the ultraviolet, to be next to it. So in fact, this is Vib Gior. This end of the spectrum is in fact about 750 nanometers, and this end of the spectrum is about 350 nanometers. So it's a very, very, very small slither. Now, the G is gamma rays, the X is X rays, the U is ultraviolet, the V is visible, the I is infrared, the M is microwave, and the R is radio waves. And not only that, I want you to understand that this side right here, this is all associated with short wavelength, which is lambda, high frequency, which is F. It's also associated with high energy, and that's from E equals H times F from quantum mechanics. And it's also associated with high temperature, and that's from Wien's law. So that's why the temperature is high at this end. The other end, on the other hand, is long wavelength. It is low frequency. It is low energy. And it is low temperature. Okay. And not only that, there's a baby wave equation, which is written as V equals distance divided by time. And if you stood on a pier, for instance, with a crest of a wave directly under you and you started timing, you hit a stopwatch and started at the time, and you waited for the next crest to get right under you, and then you stop the time, then the wave will have moved one wavelength, because that's the difference between adjacent peaks. So that's the distance traveled, and it would have done so in a unit of time called the period of oscillation, and we use a capital T for that. Well, we also know that frequency is 1 over the period, so we can also say V is equal to lambda times F, and that's what we call the baby wave equation. And this is a calculation you should be able to do. So I can ask you, for instance, what is the wavelength of AM 850? And then I could ask you, what is the wavelength of FM 93.7? Okay. The big trick here, and this is something you got to commit to memory because one, you have to know this electromagnetic spectrum. This is something you need to commit to memory. Those orders, those parts, and know that the left-hand side is small wavelength, high frequency, high energy, high temperature. The right-hand side is large wavelength, low frequency, low temperature, low energy. And then you also need to know that VibGyor is that way, and that's I'm not going to bother you with having to memorize the 350 and the 750 nanometers, but that's normally the case. But when someone tells you it's an AM radio, that means the waves are not sound, they're radio waves. And since they're radio waves, they're part of the EM spectrum. And all of these waves at the EM spectrum travel at V equals C, which is approximately 3.0 times 10 to the eighth meter per second. That's 299,792,458 meters per second. So, using the baby wave equation, we see that lambda is supposed to be V over F. And here's the part you got to memorize. If you're talking about AM, then the radio station, the 850, is the frequency in kilohertz. So we're going to say 3.00 times 10 to the eighth meters per second divided by 850 times 10 to the third. And it's 10 to the third because I said it's kilohertz. So it's 10 to the third kilohertz, or excuse me, 10 to the third hertz. So 3 times 10 to the eighth divided by 850 times 10 to the 3 gives me 352 0.94 meters. That's like four, maybe more than four football fields long. That's literally the distance from the peak of one wave to the peak of the end of that wave. So that's like four football fields long. So I think you can agree that the radio side is the long wavelength. The other part was for the FM, it's still V over F, and it's still 3.00 times 10 to the eighth meters per second for velocity. But with FM, the radio station 93.7 and all the radio stations are measured in megahertz. So this one would be dividing by 93.7 times 10 to the sixth hertz. So when we do that one, we're going to say 3 times 10 to the eighth divided by 93.7 times 10 to the sixth. And that gives me 3.2017 meters is the wavelength. So that's the kind of calculation you should be able to do. But that's pretty much it. I will tell you that there's something called the pointing vector, and you should just know that that exists, and it's convenient because it points in the direction that energy and momentum travels with the electromagnetic radiation. And in fact, it's given by 1 over mu times E cross B. So I'm not going to test you on that. It's just something I want you to know. Time is up. You guys are free to go. I'll wait for the last person to leave in case anybody has any questions. As far as next week goes, I will be showing up at 5:30 like we're supposed to, but that's going to be just a question and answer session. That's Monday and Wednesday, but you don't have to show up if you don't want to. I'm not taking roll, but I will be here, and I'm going to let students ask me questions. And when they run out of questions, we'll log off. If they don't have any questions, we'll log off right then. But thanks for thanks for coming, everybody, and don't forget that you have to let me know about when you're taking your practice test. I mean, your face-to-face test 3. Most people have done it, but I still have a few that haven't. And you ultimately need to let me know, which I'll make some announcements about tomorrow, when you're going to take your face-to-face final exam. because I'm going to offer you some Zoom sessions for that. But have a good one. I'm here till the last person leaves. Thanks again for coming, everybody.
Hi, Mr. Younger.
Yes, ma'am.
I put my appointment for tomorrow at Norfolk at
Okay.
2 p.m.
2
And
p.m. Norfolk tomorrow.
yeah, I just I don't know if they have the test or not, but
I just sent it yesterday because no one
okay,
had
okay,
signed up yet. So I had a student email me say, "Hey, I called the testing center and they said they didn't have anything about it." So I sent it yesterday. So hopefully they
okay,
should have it now.
okay, awesome. Thank you.
All right, you're welcome.
All right.
Anybody else here? I think that was it. All right, well, that's it. Thanks for coming, everyone. Have a good day. Learn a lot of physics, solve a lot of problems. Ask me for help. See ya.